I'd like to show you my self-made wooden grasshopper escapement clock, made as close as possible according to the principles of John Harrison. The main ideas were, first I wanted to build the movement almost entirely from wood. Only very few metal parts are needed. Second, I wanted to build it entirely by means of hand tools, such as a jigsaw or files, and strictly no CNC machining, no 3D printing, no laser cutting or whatsoever. Even no CAD design was needed, just a few of hand sketches and self-drawn templates like this one, showing the overall dimensions of the clock. Third, no lubrication at all. Oil is strictly forbidden. No oil is needed to keep this clock running. And this was achieved by reducing sliding friction wherever I could. I'll show you later on how. And of course, by means of Harrison's signature grasshopper escapement. Because a conventional escapement, like a Graham escapement, always has sliding friction. When the pellets are hit by the teeth of the escapement wheels, you always have friction between the tip of the tooth and the pellet. And here instead you have articulated pellets with claws, and these catch the tip of the teeth, then rotate about it and get released again. So no chance of sliding friction to occur. And where there's no friction, no oil is needed. This here is my very first hand sketch showing the overall arrangement of the clock and of the drivetrain. To further reduce friction, the drivetrain itself consists of only one single wheel, the great wheel or minute wheel, and one driven lantern pinion. The most important thing to read intuitively from the clock are the minutes. So there's only one minute hand rotating clockwise, and the second wheel or escapement wheel and the hour dial rotate anti-clockwise. But to keep the normal way of reading from left to right, seconds and hours are shown by a fixed hand against a rotating dial. This here is a small design mock-up model I made just to prove the ease of assembly and the arrangement and the readability of the dials. In a quarter of the original size. The design of the front plate has slightly changed since, to lead to a more clear and organic design, not to distract too much from the function and the moving parts of the clock. Talking about the sources I have used. This little book here, simply called Harrison by Jonathan Betts, would be perfect for the beginner. Harrison, shown here on the famous king portrait, who lived from 1693 to 1776, built some of the most precise clocks and watches of his time, and finally made it possible to measure the longitude at sea. He's most famous for this achievement. But before he built his famous sea clocks, like here for example the H1, he, being originally a carpenter, had built some long case clocks entirely from wood, like this one. And here, this little sketch shows the basic principles of Harrison's design. Wooden wheels lantern pinions, his unique grasshopper escapement, and anti-friction wheels, where the arbor of another wheel rests on and such can rotate without sliding friction. This pamphlet here, Perfecting the Harrison Twin Pivot Grasshopper Escapement by David Haskin, can be found on the internet. I do not fully agree with everything he writes, for example, about setting the clock in motion. But his tutorial here, how to design a geometrically correct grasshopper escapement, depending on the geometrical settings chosen, has been a tremendous help for me while designing a geometrically correct escapement. I have transferred Haskin's geometrical tutorial into an Excel spreadsheet and have calculated some 7 variants until I have found a geometry that was suitable for me with some 5 degrees of pendulum amplitude and escapement wheel with 120 teeth. This here is maybe the best source available, John Harrison's Contrivance by Stuart Harrison. He describes in great detail the development and design of Harrison's last pendulum clock, the famous RAS regulator. And it even includes many calculations needed for designing a Harrison type clock, and even a full set of reverse engineering design drawings, for, in this case, for the RAS regulator. And finally, this wonderful book here, The Proceedings, Harrison Decoded. It's edited again by Jonathan Betts, who was the curator of the Royal Observatory at Greenwich and the one who regulated the Burgess clock B, shown here, for the world record attempt. And the Burgess clock B bears the world record for the most precise pendulum clock swinging at free air, and it had been built entirely according to Harrison's principles. And this book here is absolutely priceless for setting up and regulating a Harrison-style pendulum clock, and for explaining the cross-coupled thermometric and barometric compensation Harrison had used, and which is still not fully understood by many. Talking about the materials I have used. All the wheels and pulleys have been made of fine layered beechwood multiplex. But for all the bearings and the rotating rollers of the lantern pinion, I have used lignum vitae, like also Harrison did. Lignum vitae, or Guaiacum officinale, is a tropical hardwood and is one of the densest and hardest woods that can be found on Earth. It's even heavier than water, and it's saturated with resinous oil that doesn't change its properties over time, and which gives it excellent sliding properties, even better than Teflon. Wonderful stuff. And I can't get enough of the wonderful smell of it. It always reminds me of gingerbread spices such as vanilla and clove. And it's so oily that even the sawdust is no dust, but more some kind of sticky, oily dough. It turns absolutely beautifully. I love this material, but the only problem, it's a tropical hardwood, and nowadays it's listed as an endangered species, so it must not be traded anymore. And the best way to obtain lignum vitae sustainably and legally is to buy some vintage objects made from it, such as these Skittles balls from Austria. They're antique, they're maybe 200 years old, and they must have gone through thousands of hands, but amazingly you still can smell this wonderful gingerbread smell of the lignum vitae. Wonderful stuff. Another rare material I used for the pivots of the arbors, for the pendulum spring and for the knife's edges of the anchor is beryllium bronze or beryllium copper. Also a very amazing material. If you glow and quench it, it gets soft. It even looks like copper and you can easily work with it and machine it. But if you temper it at 300 centigrades for roughly 3 hours, it gets hard, like hardened steel. It's a wonderful spring material. And it gets so hard you can actually cut glass with it. Only problem here, the dust and the fumes of it are highly toxic due to the beryllium, but the solid parts are totally harmless. I have put some effort in optimizing the shape of the teeth. And I have written an Excel tool again to calculate and optimize the contact geometry. I've calculated not less than 11 different variants until I found an optimal one. And you can see an animation how the contact point moves over the flank of the teeth before it jumps to the next tooth. Then I have transferred this geometry to a simple template, 10 times bigger than the original size, and I have built a simple pantograph router to take this shape and transfer it to the teeth of the wheel. The pendulum is the only major assembly of the clock being made entirely from metal. It's a temperature compensated pendulum similar to the pendulum invented by the Bavarian clockmaker Franz Josef Mahler. He, however, had the compensation mechanism at the lower end of the pendulum and moved it to the top, requiring less space and causing less air drag. When it gets warmer, the pendulum rod, which is the only part of the entire clock being made from iron, expands, lowering the pendulum bob and making the oscillation slower. But these two brass wires expand more than the pendulum rod, and by means of this lever mechanism, these two rocker arms with the brass balls are lowered, and by lowering the center of gravity of the pendulum, they accelerate the oscillation, in fact. Because I flipped it from the bottom to the top, the effect is also inverted. This, by the way, is big fun to calculate. And by screwing these brass balls in or out, the effect of the compensation can be precisely and steplessly regulated. The pendulum spring, being made from a sheet of beryllium bronze, is clamped between these two cylindrical cheeks. This is similar to the arrangement by Christian Huygens, but Huygens had cycloidal cheeks and Harrison insisted on cylindrical cheeks. This weird looking thing here is the remontoire, wind-up mechanism. I concentrated everything ugly or electrical on a separate bridge, not to clutter the movement with these kind of things. The pulley is driven by a synchronous geared motor, and to switch it on, here on top we have a reed contact which is triggered every hour by the great wheel of the movement, and then it starts to wind up the drive weight, and if it has risen enough, another reed switch down here stops it again. And this mercury switch here is just emergency cutoff in case one of the two reed contacts should fail. And the entire mechanism is suspended in felt pads in order to decouple it acoustically and dynamically from the rest of the clock. So now let me show you how to assemble the movement. Let's start with the back plate with the 4 pillars. Here on top we have an agate plate with a V-groove for the anchor. And these are the anti-friction wheels on a separate bridge. They have hubs made from lignum vitae running on pins made from beryllium bronze. And down here we have a bushing from lignum vitae for the great wheel or minute wheel. Well, and the wheel is just a wheel with 120 teeth and a pulley here for the drive cord, 2 pins to move the hour dial, and the pivots are also made from beryllium bronze. And let's just drop it in. Maybe this is one of the easiest movements to assemble because there's only one arbor to be fitted. This here is just a small latch to lock the movement when hanging on the weights. And now I shouldn't forget to also put in the endless rope for the drive. And here goes the front plate with the hour dial already fitted, like this. Well, and that's basically it. And everything is held in place by means of these 4 little wooden wedges. So no screws needed here. So that's all. This is the escapement wheel, 120 teeth as well. So 1 minute from spoke to spoke. It revolves once in 4 minutes. Here we have the lantern pinion with revolving rollers made from lignum vitae. And since this one is just floating on the anti-friction wheels, it just can be dropped into the movement like this. Now the movement can be simply hung in, this. No tools required for this either. By the way, every full hour and half hour it's possible to set the hour, so no need to stop the clock for changing it to daylight savings time. And finally we can hang in the endless rope of the Huygens type remontoir. Of course, the most essential part is still missing, the anchor of the grasshopper escapement. It has a nice edge bearing, so these knives here from beryllium bronze are rocking in the V-grooves of the agate plates. The articulated pellets are carved from snakewood and finely balanced, as you can see. So they fall back when they are released by the escapement wheel, and then they are catched by the so-called composers, these little brass flaps here. And since it's only sitting in these grooves, you can just drop it in like this. Oops. Here we go. And after hanging on the weights, we should be good to go.